network. Okay? It is a layer 2 protocol. Just like PPP, HDLC, frame relay is a data link layer protocol. All right? It's very similar to HDLC. In fact, frame relay is a subset of HDLC. HDLC is the default encapsulation on point-to-point serial links for Cisco. And it uses something called LAP-F, Link Access Procedure, for frame relay. All right? Essentially what happens is, and a lot of people don't realize this, but frame relay only runs from the router, which is your DTE device, data terminating equipment, to the frame relay switch at the edge of the provider's network. It is not an end-to-end protocol. What's happening inside the cloud? What are we doing inside the cloud? We're routing. Now it looks like it's end-to-end because we set up these things called PVCs, permanent virtual circuits. Permanent virtual circuits. We'll talk about that in a little bit. But frame relay is really just an encapsulation protocol. It allows us to encapsulate data from one end of the service provider's network to the other end of the service provider's network. DTEs are generally considered to be your terminating equipment. Usually it's your router at your location. Yeah, go ahead, a couple of chapters. A little bit more, a little bit more. Almost there. Keep going, keep going. Hurry up, let's go.
You have to wait for me.
There you go. All right. So a DTE device is your router. In fact, I think that was on the first test, or was it on the second test? The most common form of terminating a device is a DTE device, but all right. We call these routers that terminate frame relay, we call them FRADs. Yo, FRAD. What's up, FRAD? Frame relay access devices. That's not on the test. It's just an interesting thing to know. Basically, all a FRAD is a specialized device that terminates a frame relay virtual circuit. But it's not really that specialized. It's just a router running frame relay encapsulation. Frame relay is actually really, really simple to configure. There are a couple of things you need to know about frame relay. There are some rules that you have to follow, some general concepts, but we'll see that as we go through the rest of this chapter. The connection through a frame relay network is where we create this virtual circuit. So it looks confusing as heck if you look at this diagram here, but in reality, this is what it looks like to the consumer. A customer that is purchasing frame relay services, it looks like this router is directly connected to this router, or this router is directly connected to this router. Okay? The customer doesn't see all this garbage in the middle because that's hidden. We have frame relay encapsulation running here. We have a virtual circuit that runs through the cloud. And these routers actually look like they are connected point to point. And this guy should have been drawn down to here. The virtual circuit that gets created in the cloud is called a PVC, Permanent Virtual Circuit. SVCs are typically used for ATM, asynchronous transfer mode. We use PVCs for frame relay. Now again, what layer does frame relay operate at? Layer 2. So it's like you're putting a switch in the cloud. So the router on the left with Del C249, we'll learn what a Del C is in a little bit. The router on the left with Del C249 is actually even in the same subnet as the router on the right in Del C319. Because frame relay is layer 2, we share common IP information. Every PVC, every point-to-point PVC is like a different subnet though. So the bottom two routers, Del C 249 and Del C 624, those routers are going to be connected through a separate PVC on a different subnet. When you have just two routers connected, this is what we would call point-to-point frame relay. These are basically just separate networks. It is possible to do something called multi-point frame relay, where this might be a blue Del C, and this router here has a PVC that goes over to here, but it also has a PVC that goes down to here. That's called multi-point frame relay. I think we'll actually see a diagram of that a little bit later on. Hey, there we go. How about that? Amazing. All right. The FRAD, or the router that's connected to the frame relay network, can have multiple virtual circuits that go to multiple points. This is the multi-point side. These are the point sides. Now, there is a problem, and this is what's tested on, with multi-point frame relay. There's two ways to terminate multi-point frame relay. You can have a router with an interface, S0, and all of the PVCs terminate on that interface. And then you've got your remote routers connected to the frame relay network. The problem with this design is that. What is that? Split horizon. What is the concept of split horizon?
Can't remember once it came.
I cannot advertise a network out the same interface that I learn about it on. So if I've got network X over here, this guy's advertising network X. I'm not going to re-advertise network X to those routers. You follow what I'm saying? My diagram is really crappy, but you get the general idea, right? Because these guys are not connected to each other. They communicate through the corporate router to talk to each other. How do we fix that split horizon issue? What we do is we switch from multi-point frame relay to point-to-point. S0.1, S0.2, S0.3. What am I creating? Subinterfaces. So each PVC attaches to a subinterface. It's still the same physical wire, but it's a logical subinterface. So now when this router up here advertises network X, it can come in here, it can be advertised back out, those interfaces, because they're logically different interfaces. That's how you solve split horizon issues in multi-point frame relay. You make it point-to-point. What's the downside to that? You're going to need a separate network for each one of those point-to-point links, so you use more IP addresses. Of course, the other solution would be to do something like this, just add a PVC from here to here, and add a PVC from here to here, and add a PVC from here to here. That's called a full mesh. It would look something like this. If I was to draw it flat, it would look like this. If I have a full mesh, everybody just advertises themselves to everybody else. We don't have to repeat information. Okay? All right? So two ways to implement frame relay. You can implement frame relay as a point-to-point solution, or you can implement frame relay as a multi-point solution. Each endpoint needs only a single access line. That's the thing about frame relay. Because it's basically trunking, it's like router on a stick, essentially. Remember, frame relay is layer 2. So just like a router on a stick, where I can have a router interface with multiple sub-interfaces, I can do the same thing with frame relay. All right? You could do it this way. You could say, okay, here's a router. Here's serial interface S0. Here's serial interface S1. Here's serial interface S2. And you can have these guys connected on the other side, and your PVC goes across. That's point-to-point, but that's literally point-to-point, isn't it? Because you're not saving any resources there. You're actually allocating a separate physical interface for each frame relay circuit. How many subnets do we have in that scenario? 3, right? Okay. What if I had this scenario where I've got 3 routers? Here's my frame relay cloud. And I take a PVC there, a PVC there, and a PVC there. If this is a multi-point interface and these are point-to-point, how many subnets do I have in this case? Just S0. Just S0. No sub-interfaces, no separate physical interfaces. Everybody shares a common subnet. One subnet. Think about it. It's kind of like this. A switch with a router connected and 3 routers connected. Isn't that one subnet? Whereas, as we saw before, with sub-interfaces, S0.1, S0.2, S0.3, cloud, outer 1, outer 2, outer 3, we have these PVCs, but they're tied to sub-interfaces. That's like a VLAN. That's like taking a router with a trunk, and then the other sides are in VLAN 10, VLAN 20, VLAN 30, and this is a trunk, and we do encapsulation on that link. It's the same concept, only we don't do tags, right? We use something called delcies. You guys follow what I'm saying? All right. Now, it says here, more savings arise as the capacity of the access line is based on the average bandwidth requirement. So that's the other thing you need to understand about frame relay. Frame relay has been around for many, many, many eons. Not quite that long, but pretty long. Where bandwidths were not always, bandwidths didn't have to be like a gig or 100 meg or even fast Ethernet. In fact, typically with frame relay, you're dealing with bandwidths of kilobytes. 512 kilobytes, 768 kilobytes. Okay? That bandwidth requirement is called a CIR. Does anybody know what CIR stands for? No, that would be CIDR. CIDR. CIR stands for Committed Information Rate. Another term you need to know about frame relay. When you go to a service provider and you buy a frame relay PVC, you tell that provider, I want a guaranteed bandwidth across that PVC. That guaranteed bandwidth is 512K. That is called your CIR. That's what the provider has committed to guarantee. Can you go above that? Absolutely. But if you go above that CIR, you're going to get charged a premium. It's kind of like buying a phone plan. You're guaranteed a certain number of minutes a month. The phone doesn't stop working if you run out of minutes. But if you go over, you have to pay for additional minutes. Of course, the young guys don't know what that's all about. because now all the minutes are unlimited, but it didn't used to be that way. All right, you used to have these night and weekend minutes. Remember that?
Yeah.
Right?
Free on the weekends. Free on the weekends. Unlimited on the weekends. That's what it was.
Unlimited on the weekends and after 9 p.m. You can make as many calls as you want. But during the day, you had to pay extra. And he actually shook his head and said, no, I don't remember that at all. We pick on the young guys.
My first internet bill was $297.
No, I've had bills much higher than that.
Well, that was just me by myself on one computer. That wasn't a company.
No, I mean, I've had bills much higher than that because of what I was doing on the internet.
It involved a credit card.
Yeah, it did involve a credit card. It's not that. Okay, so here's our frame relay header. Not something you need to know for the test. You do need to know that Cisco supports two types of encapsulation in frame relay, IETF and Cisco. And which one do you think is the default?
IETF.
Nope.
Nope.
If Cisco has a choice of doing their own encapsulation or somebody else's, who are they going to do by default? They're going to do their own.
Yes.
Okay? And of course, Cisco's method of encapsulating frame relay is not nearly as efficient as IETF. Now, there's a whole bunch of stuff in this frame relay header. There's something called the delc. There's another thing called the delc. There's these feckin bits. Those feckin bits are crazy. And then we have Beckon bits too. Beckon bits.
From myself all the time.
Yeah. If it has Beckon bits, it's yummy.
What's in the bag? I can't.
That stands for forward explicit congestion notification, backward explicit congestion notification. These bits here, this Beckon bit, the Beckon bit, the DE bit, these are all used for QoS and frame relay, which is not very good, because about the only thing a frame relay can do for QoS is say, we're congested. And DE stands for discard eligible, meaning now I have to start dropping your bits because we're congested. So there's really no prioritization in frame relay. That's why MPLS became very popular, because MPLS actually has a 3-bit field for QoS. Frame relay didn't have QoS. Okay? It had a very rudimentary way of managing flow, but it didn't have a way to prioritize. All right, what are the flag fields here? The flag fields here, that's my preamble and postamble. So really those don't count. There's my header, which is 16 bits. There's my FCS, my frame check sequence. That is my CRC, my cyclic redundancy check. Of course, the data field is what? Layer 3, layer 4, my payload, right? IETF encapsulation is not the same as Cisco. So if you're running a Cisco device to a non-Cisco device, you have to run IETF. Cisco to Cisco, you can run the Cisco encapsulation. All right? So terms, just like we learned with routing protocols, we have terms. The delc. This is called the data link connection identifier. Let me explain what a delc does, because that is definitely something you're going to have to know for the test. You've got a router with a serial link. You've got your frame relay cloud. You've got another router with a serial link. I've got a PVC that goes there. I've got a PVC that goes there. There's an IP address on that interface. There's an IP address on that interface. There's an IP address on that interface. Routers care about what? Routing. IP, right? Routers care about routing. So if you've got network A, and you've got network B, and you've got network C, What does the routing table on R1 look like? It's going to say A is a connected route. I'll put little quotes there. B, go to dot 2, and C, go to dot 3. You guys agree with that? Shake your head, yes. Okay. Routers care about routing to next hops. The frame relay network is an afterthought because it's layer 2. So when the router wants to route to dot 2, it's going to generate a packet to go to dot 2. But before that packet can be sent out, it has to be encapsulated. It has to be put inside of a frame. And in this case, that frame is a frame relay frame. Who cares about frame relay?
Cloud.
The cloud. The people in the cloud care about frame relay. There has to be a way that when that packet arrives at the frame relay switch, that the provider knows to send that packet this way or to send that packet that way. And that is where the DELC comes into play. Each one of these PVCs has a number, 101, 100. So when the router 1 encapsulates the frame, in the frame relay header, it puts in the DELC. We'll learn how the router learns about that DELC later on. So that's almost like a tag or like a destination MAC address. So router 1 says, oh, I want to go over to the .2 subnet. I'm going to tag that frame in 100. So when the provider receives that frame, it knows to send it over that pipe instead of sending it over that pipe. So what is the relationship between a DELC and an IP? The DELC is local, and that maps to a remote IP. From router 1's perspective, the DELC is local, and it maps to a remote IP. At least 3 questions on the test about that concept alone. Local DELC maps to a remote IP. All right? It's a 10-bit value. CR, not used. Those dang feckin' bits. Forward explicit congestion notification. Here's the way feckin' and beckin works. It's just a way for the routers to know that the frame relay network is congestion. I'm just going to do 2 routers this time. Okay. This guy's sending over frame relay. The provider has the ability to mark those frames with a feckin' bit. And what that's going to tell the receiving router is, hey, the frame relay network is congested. So expect to only get your CIR. That's why it's called explicit congestion notification, because we're marking a flag that tells the receiving router the frame relay network is congested. Backward explicit congestion notification is marking the return frames that go back to the source with a beckon bit that tells it that the frame relay network is congested. You're not tested on that, or that, but that's what it's for. Discard eligible. This is how the service provider manages their network. You have a CIR of 512K. You are guaranteed 512K. But how fast is a T1 line? 1.544 meg. So you can actually exceed that CIR. You can double it. which is allowed. You're going to pay for that, but it's allowed. So you start sending out your data at a max bandwidth of 1.5 megs. As long as the frame relay cloud is not congested, that goes through, and they charge you a premium. But as soon as that cloud gets congested, you get throttled down to 512K, and anything above 512K gets marked discard eligible. And the frame relay provider has the ability to delete those or drop those frames. That's what discard eligible means. Hey, you wanted to do frame relay, man.
So the CR really doesn't mean anything.
CR literally doesn't mean anything.
It's not defined.
It's not defined.
So we don't even know about it. Or do we just need to know it's not defined?
You don't need to know anything about it.
Good.
The only thing you need to know about on this table is the DELC. And quite honestly, frame relay is a dying protocol.
AT&T still uses it quite a bit.
There's a lot of people that still use it, but it is a dying protocol.
Verizon's doing VPN.
MPLS VPNs, yeah. Okay, it's a dying protocol because it doesn't do QoS. A DELC identifies a logical virtual circuit between the customer premise equipment, which is your router, and the frame relay switch. DELCs are locally significant. That's important to know for the test, meaning that the DELCs don't have to match on both sides of the PVC. The analogy I use, if you're driving down the highway and the highway splits and you see a sign that says LA left and San Diego right, do you care what the sign at the other end of that highway says? No. You only care about what the sign is as you enter the tunnel. Now there are some reserved DELC addresses. I put them on here even though you don't really have to know them. So this is really the range of DELCs that you're going to see, 16 to 1007. Again, not something you're tested on. A DELC allows us to map what to what? Local DELC to remote IP. We already talked about what committed information rate is. What is local access rate? It's something you definitely have to consider when you're dealing with frame relay. Local access rate as opposed to committed information rate.
Right between you and the beginning of
The rate between you and the cloud is your local access rate, which is a physical circuit. And then the rate in the cloud is your committed information rate, right? I talked about that. A router has a serial link, that's a T1, that's 1544 KB. But in the cloud, you might have a PVC that's 56K. And yes, we still see PVCs of 56K. The nice thing about frame relay dying is that it's cheap because nobody buys it anymore, supply and demand. So if you want to get a cheap circuit to do data transfers at night or something like that, you can do that. Now, committed information rate doesn't mean you're committed to that rate. Committed information rate means the service provider is committed to that rate. They have to guarantee that bandwidth. Most of the time, customers will buy a CIR of 0. Why would they do that? They only pay for what they use. It costs a little bit more, but in the long haul, they're not paying for stuff they're not using. The downside to doing a CIR of 0 is that all of your bits can be marked discard eligible, which means anything can be dropped. Whereas if you have a CIR of 128K, only 128K can get dropped. I mean, anything above 128K can get dropped. Another aspect of frame relay that you guys need to know about is this thing called local management interface. It is a protocol. 3 different versions, Cisco, ANSI, and Q933A. Which one do you think Cisco uses by default? Cisco, yeah. So here's how LMI works. You've got a router with a circuit going to a frame relay cloud, another circuit going to another router, okay? You've got network X back here, you've got network Y over here. Del C 100 here, I'll put Del C 200 here. All right? The only thing that you actually technically have to configure on the router is one command, encapsulation frame relay. That's the only command you have to put on that interface because everything else happens automatically. And that happens because of LMI. So as soon as frame relay is running on this link, messages start going back and forth between the frame relay provider and the router. The first thing that gets advertised is the Del C gets advertised to the router. The second thing that happens is the router sends an inverse ARP to try and figure out, or try to announce itself to the other router. So when that inverse ARP comes over here, this router says, oh, dot 1 is on Del C 200. This guy sends an inverse ARP. Oh, dot 2 is on Del C 100. That's called building a frame relay map. The nice thing about frame relay is that all of this stuff happens automatically. It's almost like establishing a VPN tunnel because frame relay is technically a VPN technology. There's no confidentiality because we don't have encryption, but it is a virtual private network. Our traffic is literally being tunneled. So LMI is used to determine the status of the frame relay circuit. This is on the test. Very important. 3 states that a PVC can be in. Active, that's a good state. Active is great. If you deal with BGP, active is bad, so just remember that. And frame relay, active means everything is working. Inactive indicates that the local connection to the frame relay is working, but there's a problem on the remote side. That's on the test. A PVC state of inactive means that the local side is working just fine, but there's a problem on the remote side. Deleted means nothing is happening on the local side. So I need to troubleshoot local frame relay. Right. Another concept in frame relay is building these maps. Again, what are we mapping in frame relay? Del C's to IPs. Specifically, what kind of Del C to what kind of IP? Local Del C to remote IP. Remember I said that's so that we can identify that if I want to send traffic to this router, that's Del C 1, or I want to send traffic to that router, that's Del C 2, when the router generates the frame, it needs to tag that frame 1 or 2, so that when the frame relay provider receives the frame, it knows to send it that way or that way. So this local Delcy is mapped to a remote IP. Those Delcy, those maps can be configured manually, or they can be discovered through the inverse ART process. Why is it called inverse ART? What is the goal of ART? To take a known IP address and discover a layer 2 address. Well, in this case, we know the layer 2 address, that's the Delcy. We have to figure out who's on the other side, that's the IP. So it's the opposite. All right, I don't really want to get into a whole lot of detail with inverse ART, but not that important. So now the only thing left is to talk about how do we implement frame relay. It's actually very simple. It's a single command, encapsulation frame relay. Encapsulation frame relay. Packet Tracer actually supports frame relay. I can show you real quick how simple it is to set up frame relay and Packet Tracer. Let me get rid of all this junk. I've got a router here. Let's go ahead and grab another router.
Actually works now, because I mean, we did that in 2011. We had to fake it out. If I remember correctly.
It works, yep, because they've got this thing called a frame relay switch now. Where is it? It is right, where the heck is it? So small. So small, man. Hey, I think this is it. Yeah, frame relay. So you just grab one of these little happy clouds. And what you have to do in the happy cloud is you have to map your Delcies, right? Serial 0, we're going to go ahead and oops. Should be able to pick a number here.
Is that it for?
Let me connect them first. I might have to connect them first. Oh, I got to add a serial link to my router here. Hold on. Let's do a 2W. Let's do a 2T. Not 1T, that's good. Turn that back on. And same thing here. 1T. Okay, to turn it off, dang it. It makes you actually turn the router off.
That's okay.
Yeah. Serial, yeah, it looks like you have to connect them first. Serial 1, serial 0. Now I can go to my cloud, go to frame relay, and I should be able to add serial 0. Oh, there we go. Delcy 100, name left. LMI, let's go ahead and use Cisco. Add, and then Delcy 200, we'll call that right. Add that. Now I can go to my frame relay. I don't know why the heck this is all jacked up. So left to serial 1, which is on the right. Why is that serial 0 to serial 0? Oh, I know what I did wrong. Stupid me. I added 2 Delcies to serial. I don't want to do that. I need to add, because I use serial 1. So that's 200, that's going to be on the right. I said it was so simple, didn't I? That's left, serial 1 is right. There we go. Now I have that. So I said, basically I just built my PVC through the cloud. And now I'm done. I just have to go into the router on the left. Config T, interface serial 000, IP address 1.1.1.1, 255.255.255.252, shut, encapsulation, frame relay. Okay, you can go to the router on the right. No. Config T, interface serial 000, IP address 1.1.1.2, 255.255.255.252, shut, encapsulation, frame relay. And look, it came up. Ping 1.1.1.1. I can ping across the frame relay network. And I can do show frame relay map, which is, by the way, the command you need to know for the test. And I can see that the PVC is active. It was dynamically created. It supports broadcasts. Del C 200, which is the Del C on the right, remember? Del C 200 maps to 1111, which is the IP address on the other side. Follow me? So on this router, I should see Del C 100 maps to 1112. Show frame relay map. And sure enough, Del C 100 maps to 1112. So technically speaking, the only command I actually did related to frame relay, besides setting up the cloud, which is the service provider, is encapsulation frame relay. Everything else happened automatically because of LMI and inverse ARC. Everything gets discovered automatically. Now I'll leave that open so we can look at some other things as we're going through the lecture here. But encapsulation frame relay. Now, you can specify Cisco or IETF. Obviously, we know we're using Cisco because that's the default. So if you don't specify a method, it's going to use Cisco encapsulation. And you can also specify the LMI type. One of three choices. What would force you to decide to use one versus the other?
Just go.
Depends what the service provider supports, right? Because isn't LMI you exchanging information with the service provider? But I will say that 99% of the service providers are going to support Cisco. That's what I just created. I didn't use the same IP addresses. By the way, what kind of frame relay configuration is this? Point-to-point frame relay, right? Local Del C maps to remote IP. Local Del C maps to remote IP. I keep saying that over and over again because you need to know that for the test. All right, so make sure your interface is enabled. Make sure that you're receiving the Del C information. If you're not receiving the Del C information, you can actually go into the interface. I don't know if this works in Packet Tracer, but we'll give it a shot. And you can say frame relay interface Del C. It doesn't work, but you can actually assign it manually. Okay? Oh, okay. It does work. Just without the Del C keyword. That's actually correct. I mistyped that command. Define a switched or terminated delcy. So you can statically define the delcy. I think there's actually a command with the delcy also. All right. But really, when it comes down to it, that gets advertised automatically. That gets advertised automatically. LMI sets up the actual circuit, and then inverse arc allows us to discover each other. So everything happens automatically. It's very simple. It is a pretty basic protocol. Show frame relay map. That is the command that you're going to use on the lab. So on the lab, they're going to ask you a question like, what layer 2 address will I use to reach 1.1? And the answer would be 101. Yep. Because a delcy is a layer 2 address. It's like a MAC address or a VLAN tag. Remember what active meant? Active means yay. Dynamic means that this frame relay map was created dynamically through LMI. Broadcast means that broadcast traffic is allowed to go over this PVC because frame relay is kind of like a pseudo broadcasting network. It can or cannot support frame broadcast depending on the service provider. All right. If you have to create a static map, you can create a static map. So let's say for some reason LMI is not working. It's like saying a dynamic routing protocol doesn't work. So you can do static routes. Frame relay map, IP 1.1.1.2, 100, broadcast. What does that command do?
You created the map.
I mapped the local delcy to the remote IP. And I said that we can send broadcast over that map. So if I do a show frame relay map, now you can see it's static. It's down because I used the wrong delcy. But you get the idea. I'm on the wrong router. I was supposed to do that on the other router. Okay. By the way, deleted, that tells me there's something wrong on the local side. Yeah, there is something wrong on the local side. You don't have delcy 100, you idiot, right? You have delcy 200. A static frame relay map is like a static route. So here we did encapsulation frame relay. We're assuming that inverse arc doesn't work, LMI doesn't work, so we're going to put in our static map. 0.2 is the remote IP. 110 is the local delcy. Broadcast means we can send broadcast traffic, and Cisco is the encapsulation type. That is actually redundant. You don't have to specify Cisco since it is the default. All right. You can also specify multiple maps. This would be if it's a multi-point frame relay interface. Multipoint means you have several PVCs that terminate on one interface.
Scott, could you also do that on subinterfaces, each one being a subinterface?
Yes, but then that would no longer be multipoint, that would be point-to-point.
Okay.
Multipoint is when multiple PVCs terminate on the same interface. Point-to-point is when, and by the way, you can also do combinations, right? I could do something like this where I have serial 0.1 and serial 0.2, and I have 3 PVCs. 2 of the PVCs terminate to 2, and this PVC terminates to 1. So that's point-to-point, and this is multipoint. it's still multi-point because there's two PVCs going to one interface. So you can kind of have all kinds of different combinations of these frame relay configurations. What does the status of active mean? Yay. I got mail. Yay. You guys remember that show?
Yeah.
Okay. Good stuff. Are you guys online catching any of this? Everybody's very quiet today. I don't know why. Everybody seems very quiet today. I guess they're just worn out. After staying up till 2 or 3 in the morning every day, I can understand why. I mean, there isn't a whole lot else to talk about with frame relay, guys. Show frame relay map, that's what you're going to be doing on the test. It's literally that simple. If they say the address is .3, look for the map to .3. If they say the address is .4, look for the map to .4. Don't forget this command, and don't forget the dash. Command doesn't work without the dash. All right. Here they're talking about split horizon, where I have a multi-point frame relay configuration. By the way, split horizon only applies to what protocols? Is split horizon common to every single routing protocol? The answer is no. It only applies to distance vector routing protocols. So you do not have split horizon issues with OSPF. But with RIP and EIGRP, you have split horizon issues. Split horizon means if I receive a routing update on an interface, I'm not going to send that update out the other interfaces or the other PVCs because they're tied to the same physical interface. How do I fix that problem? Stop using a distance vector protocol. No. How do I fix that problem?
Subinterfaces.
Yep. Take that physical interface. Here we go. Now you can turn off split horizon. That's not generally recommended. Take that physical interface and divide it up into sub-interfaces. What is the downside to that, though? We just made our routing architecture a little bit more complicated, didn't we?
You're actually paying for 3 different PVCs now?
There already are 3 PVCs. There's 3 PVCs already. These are the PVCs.
Okay.
In fact, the service provider could care less if you're doing sub-interfaces or physical interface. They don't have any control over that, and they don't really care. A PVC is a PVC. What is the downside to this method as opposed to this method? In this method, everybody is on the same subnet. These are layer 2 connections going to one interface. With this method, everybody's on a different subnet because they're separate sub-interfaces. We went from multi-point frame relay to point-to-point frame relay. You guys follow me? Each sub-interface is treated as a separate physical interface, even though it's tied to the same physical port. All right? 2 types of frame relay, point-to-point or multi-point. I kind of drew this before. This is a multi-point because I've got 2 PVCs that come into that interface. And I've got this PVC that comes into that sub-interface. This is on the test as well, guys. Why do I have this command? That's the command that I was actually talking about. I did frame relay interface space del C, it's frame relay interface dash del C. But why? And I didn't have to type the dash del C because it inferred that because of the command. Why do I have to specify the del C on a sub-interface? Does the service provider know what sub-interface a del C goes to? Where is the service provider sending the del C to? The physical wire. As far as the service provider is concerned, there's a wire there, and I'm sending the del Cs onto that wire. What you do with those del Cs is completely up to you. So when you have sub-interfaces, you have to map your del Cs to your sub-interfaces. Otherwise, the router's going to get confused. It's not going to know what del C goes where. If it was a physical interface, you wouldn't have to worry about it. But because sub-interfaces are separate, you have to tell the router which sub-interface gets what del C. That's the command line configuration. All right.